Let's talk about the sum and the product of roots. When you are given roots of a polynomial equation and you're asked to find that equation, you can use the sum and the product of roots formulas to help you get there. So the sum of your roots is equal to negative b over a, and the product of your roots is equal to c over a. The a, b, and c that I'm referring to are the ones from standard quadratic form, ax squared plus bx plus c. And if we had an equation, we set it equal to 0. And if we need a function, we just set that equal to y or f of x or g of x, something like that. So I wrote down what I just was saying. When you're given the roots, you can use this to find the polynomial equation. So write that down, and then I'm going to show you some examples. Now, in my examples, I'm giving you more than you probably need in order to grasp this concept, but I wanted to show you examples of ones that have real solutions and ones that don't. So let me show you what I've got for my examples. All right. So like I say, I've given you one of each for quadratic, cubic, and quartic functions. So for my quadratic examples, I intentionally picked these two because this first example has two roots that are real and rational. This would work for those, and it would also work if my roots are complex or irrational. So these are complex roots I've chosen. So you use the sum and the product of your roots. Sum means to add them together. So if you add your two roots together, for this one I have 2 and negative 5 are given to me. So if I add those directly together, I get negative 3. And I set that equal to my little formula, negative b over a. The product means to multiply. So I take the roots I was given and just directly multiply them together. And I get negative 10. Set that equal to c over a. So a is the denominator. It's understood if there's not a denominator that we put a 1 in math. So that was a little 1 that's understood to be there. So a would equal 1. B is the one that you have to change the sign of. So if negative 3 is equal to negative b, b would be equal to positive 3. And then c is equal to negative 10, this numerator right here. So then you can write out your standard quadratic form. So a is 1, so I just put x squared plus 3x minus 10 equals 0. So I can get the equation that those roots came from. Now you could also have written them as factors and just multiply that together. That would be the other way to do it, but this method would also work. So number 2, let's look at these roots. I'm given two complex roots, 7 plus I and 7 minus I. If I separate it, that's what they look like separated. So if I add those two together, it looks scarier than it really is because 7 plus 7 is 14. But notice how I plus negative I would cancel out, so they're gone. So you get 14 equals negative b over a. We'll save that until we get the other part before you pick out your letters. 7 plus I times 7 minus I is a difference of squares. These are conjugates of one another. We talked in class about how conjugates are when you have a complex root or an irrational root. You won't ever have one without the other. So 7 plus I would never be a root without 7 minus I. The square root of 3 would never be a root without the negative square root of 3, for example. So back to my example, 7 times 7 is 49, and I times negative I is negative I squared. Because you only have to multiply the first and the last, since the inside and outside are automatically going to cancel out, since that is a difference of squares. So I end up with I squared equals negative 1, so that's 49 plus 1 gives me 50. Now I can pick out a, b, and c and write the equation. So a is again understood to be 1 since nothing else is in my denominator. B is negative 14 because 14 equals negative b, then b is negative 14. And c would be 50. So you write out x squared minus 14x plus 50 equals 0. Let's look at some that are cubic. So for my cubic examples, they have 3 roots. So you're given something that's real and rational. It can also work for these. Remember, like we just said on that other board, that the other method to figure these out is to write out your factors and multiply all that together. But what if you don't like that method? You could use this method. So I take one root, it doesn't matter which one, and write the factor out and kind of save it till you finish this other part, and then you'll use it in a minute. Use sum and product of your roots for the other two to get your quadratic, and then multiply by that factor. So I just chose randomly the -2 and the 4 to find the sum and the product. So I add them together and I get 2. I multiply them together and I got -8. You set them equal to our formulas and we can pick out that A was 1, B was -2, and C was -8. So I wrote out my quadratic equation that came from those two roots. I take the original one that I didn't use yet and I multiply it all together. So make sure you don't miss a variable or a number. It's very tedious right there. So you multiply it all out, combine your like terms, and you get your cubic equation. It's cubic because you have 3 roots. So you're going to have a degree of 3 when you finish. Those go hand in hand. The other example I put on this board were ones that have complex and real solutions. So what if you're given a combination for cubic? You have 2. So 2 comes from x minus 2. We're going to save that till we're done with this first part. Then I take 4i. I know if they give me 4i for a root, I would also have -4i as a root. So you assume that that one's also there, even if they don't tell you it's there. So 4i plus -4i adds up to 0. 4i times -4i would multiply together to give me positive 16. And then I pick out A is 1, B is 0, and C is 16. I write out my quadratic, so it didn't have a B. It was just x squared plus 16. I bring over the other root that I haven't used yet as x minus 2, multiply it all together carefully, and I get my cubic equation that these 3 roots originated from. All right, one more board, and we'll be done with these. So for quartic are the big ones. They have 4 roots, so there's lots of work to be done. So what you have to do with a quartic function is take your roots in pairs. So I took 2 real roots and I added them and I multiplied them, and then I took the other 2 and I added them and I multiplied them. Then you take the quadratic, so from the first 2 roots, -3 and 3, I added and multiplied. I picked out A was 1, B was 0, and C was -9. So I wrote down x squared minus 9 came from that first pair of roots that I worked with, because you can only do sum and product with 2 roots at a time. Then I took the other 2 roots right here. I added them, I multiplied them, I pick out A, B, and C. I wrote down the quadratic equation that went with those 2. Then you multiply all that together, be careful, and you end up with your quartic polynomial equation down here at the bottom. The last example is the quartic one that's not real or rational. It has an irrational and a complex root. I intentionally left the conjugates off of here so I could bring up the point. If they give you the square root of 3, you automatically assume there'd also be a negative square root of 3. If they say 2 plus I, you automatically assume there's also a 2 minus I as your root. So again, take those first 2 conjugates, add them together, so you get 0, multiply them together, you get -3. I picked out my A, my B, and my C, and I wrote down the quadratic equation, I can't write with my left hand very well, that went with those 2. Then I took the other 2 conjugates, add them together, you get 4, multiply them together, and I got 5. Pick out A, B, and C again, write out the quadratic that goes with those 2. Again, carefully multiply it all together and add up your like terms, and you have your final quartic polynomial equation. So if you are given 4 roots, even if you're given 2 and you know they have conjugates, which would give you 4 roots, like this one, you know